Okay guys, I'm going to start by going through the homework that I gave you on Wednesday. So we did the similar triangle theorem, and then I also wanted you to do a bit of work on Pythagoras' theorem, just to check that you still remember it really more than anything. Okay, so for each question the triangles ABC and ADE are similar. Find the value of x and y in each case. Hint, use theorem 12 to help us get the required sides. Okay, so that's the similar triangle. Okay, so they said that ABC, okay, so there's A, B, C, 4, 3, and y. Okay, and they said that that was similar to, so it has the same angles as the big one, DEA or ADE. Now, so this is 2x, this is 7.5, and this is x. Okay, and they want us to find x and y. So we need to make our fractions where it's quite easy to see the corresponding sides here because they're nicely lined up for us. Not always so, but this one here corresponds with that one there. This one corresponds with that one. And the one at the bottom there corresponds with the one at the bottom there. Yeah? Okay, so I'm going to go big triangle on the top with 2x and put it over the corresponding side, which is 4. And that equals big triangle 7.5 over 3. Okay, so then I can cross multiply, so the 4 by the 7.5 and the 3 by the 2x. So 3 by 2x is 6x, and 4 by 7.5, is that 30? 30. Then we divide by 6 on both sides to isolate the x, and we get x is 5. Okay, so that means that this is 5, and that's 10. Okay, so I'm going to create another fraction. So the same one that I started with here, 2x over 4, but it's now 10 over 4. Okay, so I've got that there. And then I need to use the y, so 5 over y. Big triangle over little triangle, 5 over y are corresponding. Okay, so the 4 with the 5 and the y with the 10 gives us 10y equals 20. And then we divide by 10 to isolate the y. So y is 2. So x is 5 and y is 2 for the first one. Second one, Abby wants to measure the height of her school building. She notices that she can see the top of her building reflected in a puddle on the ground. This puddle is 22 meters away from the school building. Abby is 1.45 meters tall and she is 5 meters away from the puddle as shown. Find the height of the school building. Okay, so I'm going to draw them again. I know they're there, but so this here is the height of the school, which we don't know. This is 22 meters. Yeah. And then we have the Abbey triangle. So this is the height of Abbey. And this is 5. and we know the height of Abby, sorry, there you go. Height of Abby is 1.45 meters. Okay, so corresponding sides, the height of the school, these are just mirror images, so the height of the school matches up or corresponds to the height of Abby. The distance along the ground from the puddle. And then the right angle triangle, so the hypotenuse. So there's your corresponding sides. Okay, so I'm going to go big over little again. So I'm going to go h for the height of the school. Over the corresponding side would be the height of Abby, so 1.45 equals, so there's no point in using the red sides because we don't know them. So I'm going to go big triangle over little triangle, which would be 22 over 5. Yeah? So the 1.45 is going to be multiplied by 20 and the 5 is going to be multiplied by h. So that is 5h equals 31.9. And then we're going to divide by 5 to cancel the 5 and isolate the h. So I'm getting that the building has a height of 6.38 meters. Okay, and then the last one was Pythagoras. So find the value of x and y in each of the following triangles and answer in surd form where necessary. Okay, so we have two triangles in the lower one. So in this one here, we have two of the sides and we're missing one. Whereas in the other one, we're missing two and we only have one. So I'm going to start with this one. Okay, so c squared equals a squared plus b squared. And just so you remember, this is the hypotenuse, this is the opposite, and this is the adjacent. So the hypotenuse is x. The opposite, it actually doesn't matter, so I'm just going to go with 4 and then 7. Remember to square everything. So I have 16 plus 49, which is 65. And then I'm going to take the square root to cancel out the square and isolate the x. And the square root of 65 in surd form is the square root of 65. Okay, so this is the square root of 65. Yeah, and now if I concentrate on this triangle, yeah, the right angle is down here in the corner. I've just kind of gone over it, but it's down there in the corner. So that makes the square root of 65 the hypotenuse for the second triangle. So c squared equals a squared plus b squared again. C this time is the square root of 65 squared. A, we'll go with 8. And then b, we don't know, so we leave it as y. Square root of 65 squared, the square root and the square cancel, so it's just 65. 8 squared is 64 plus y squared. Now, a bit of algebra required. I need to isolate this y squared, so I'm going to need to move this 64. At the moment it's plus, so I'll move it with a minus 64 to cancel, and a minus 64 then for balance. So 1 equals y squared, and then get rid of the square with a square root. So y equals 1. So x is the square root of 65 and y is 1. Okay? Okay, so we go in here. I think I have 2 classes left to get through these couple of circle theorems. Okay, so it starts with all the what's the word? Keywords for a circle. So I think you know most of these. We'll fly through them very quickly because I don't want to take too much time over this. Sorry, I just have to find the right place here. My laptop has stopped freaking out though, so that's good. Pythagoras. Right, so here's the circle. And I don't know about there. Yeah. That's the center. Okay, then if we go away, insert, what colour are we in? Blue. Insert a line. So a line going from the center of the circle out to the circumference of the circle. Is called a radius. Hopefully that'll appear in a second. There you go. A line that goes from one circumference through the center to the other circumference. Sorry, I have to wait for it to catch up. That line is called a diameter. And I suppose it's important to note that a diameter, I think you know this anyway, is twice the radius. Yeah? Okay, the next one, let's go green. So if we do this, that bit in there, is called a sector. Hang on, waiting for it to catch up again. There you go. It's so slow. The bit along the bottom, I don't know if this is going to come up. So kind of like the crust of the pizza. So the sector came up there now. Yeah, and the crust of the pizza there is called an arc. Okay, and then we just have one more. Go to a different color, right. So a line that goes from circumference to circumference, just like that, but doesn't go through the center. Sorry, this is all just taking a couple of seconds, which is a bit annoying. There you go. So that line is called a chord. And then the bit that it cuts off, as in this bit in here, is called a segment. Have I forgot? Oh, okay, I have forgotten something. Hang on. I'm loading again here. The only thing I think I've forgotten is the bit around the outside. Okay, so for a circle, it's called the circumference. For any other shape, it's called a perimeter. So it is the perimeter of a circle. It's just it has a different name. So the circle, radius, chord, diameter, circumference, arc. Ooh, tangent I didn't do. Let me do a tangent. Go yellow. Okay, so that's a tangent. So a tangent is a line that touches the circle at one point only. I don't know if this even touches. No, it doesn't, but let's assume it does. So anyway, I did write those notes there. They just haven't synced across yet. That's a tangent. So it's a line. It can touch the circle anywhere, but it just touches it once. It intersects the circle at one point. And then sector we did, and then we did a few extras because we did chord and segment, and that's it actually, chord and segment. Okay, so our two theorems that we're going to do today are going to be our theorem 13 and 14. Okay, so here's 13. So the angle at the center of a circle standing on a given arc is twice the angle at any point of the circle standing on the same arc. Okay, so it sounds really complicated. It's really not. So here's your arc. Yeah? And both of these, they're not triangles obviously, but both of these little angles originate from that arc. Okay, so can you see that when I draw that? Yeah, what we have there is a sector of the circle, and its pizza crust is the same as the pizza crust for that angle. Yeah, it's just one of them stops at the center and one of them continues to the circumference. Okay, and essentially what the theorem says is that the angle at the center is twice the angle at the circumference. The angle at the center is twice the angle at the circumference. Okay? Provided they're standing on the same arc. And then the other one that we're going to do today is quite similar. It's actually not considered a theorem, it's considered a corollary. So remember, a corollary is a follow-on from a theorem. Okay, so it's not actually its own theorem, it's just a follow-on from that one. And it's very similar. It's all angles standing on the same arc are equal. Okay, so see here, you can see they've highlighted the arc. I'm just going to further highlight it. See it there? Okay, so there's the arc. And then we have So we have this one, which stops at the center. Yeah, and we know that that's going to be double this one because let's try that again. So the angle there at the center is going to be double that angle. Yeah, so the angle here is going to be twice as big as the angle here because they both start in the same arc. One of them stops at the center, one of them goes on. But it does say any angle from the same arc. So this one here, I'm going to highlight in yellow. So that also is standing on the same arc because it has the same starting points. But it doesn't stop at the center. It goes on and continues to the circumference. So the red angle would also be twice the yellow angle. Okay? And for that reason, these are the same. Okay, and I could draw 3 or 4 more, and they'd all be the same. Okay, so angles at points of the circle standing on the same arc are equal. And then angles at the center on the same arc are double the angles at the circumference. Okay, so they're your 2 theorems, but like I said, they're related to each other. So, and it leaves us with 2 more to do on Monday. Okay, so we'll have a quick look at maybe 2 questions just to show you. So in the following circle, with center O, find angle A. Okay, so angle A, I'm going to highlight my arc. Okay, so there's my arc. Angle A is the one that stops at the center. There it is there. Yeah, but I have another angle standing on the same arc. There it is there. But that continues to the circumference. They have told us that that is 50. We know that this has to be twice that. So we know that angle A is 2 times 50, which is 100. And how did we know? Angle at the center is twice the angle at the circumference. Yeah? And then what is angle B? So angle B, does it start on the same arc? It does. So it goes from that point up and continues right up to the circumference. So that means this angle here and this angle here are both standing on the same arc and they both continue to the circumference, which means they're the same. So angle B is also equal to 50 degrees because they are angles standing on the same arc. Okay, we'll try one more. So work out the measure of angle 1 and angle 2. Okay, so I'm going to pick out an arc here. So I have an arc that starts here, goes along here, and finishes there. Yeah? Now, can I pick, yeah, look. So starting at that arc, I can go up there to 60. And then starting at the exact same arc and continuing all the way to circumference, I get 2. So angle 2 equals 60 because they are angles standing on the same arc. And I have a feeling I can do the exact same thing. So if I take all that off, and this time I'm going to highlight the arc on the other side. Yeah. So I'm going from the left-hand point, now from the right-hand point, all the way up to circumference, and I find angle 1. And then from the left-hand part of the arc and the right-hand part of the arc, I get 40. So they're the same. So angle 1 equals 40 degrees, and my reason is the same. Okay? So that's the idea with the questions. Just more theorems to throw in. What will we do? What about these two? I don't want to do loads for the sake of doing loads, so I'm trying to just pick the good ones. So these two. So find the measure of each angle labelled in the following diagrams. Remember to show as much work as possible, and O is the centre of the circle in each case. Okay, so let's try these two. Okay, they're definitely, you can kind of clearly see that they're arcs, so they're definitely based on those two theorems that we just did. All right, so we'll correct them on Monday, and then I will do the last part, and then we're pretty much done with geometry. The second chapter, like I said, doesn't have a huge amount in it. All right, have a nice weekend, guys.